Welcome to the student demo for iClass at transportereducators.org. I've just logged into the conference, and the first window that I see is a pop-up window for Adobe Flash Player settings. I'm going to click Allow to allow access to my camera and microphone. Here I can play a test sound, which will allow me to listen to sound through my microphone and speakers. I'm going to play it. I can hear it through my speakers. I can also view that my microphone is working. I'm going to join the audio conference. I noticed on the top left there's a button that says Share My Microphone. I've already shared my microphone upon entering the conference, so that button is already activated. The next button I see is Share My Camera in case I wanted to share my webcam with the other participants of the conference. Over on the right is a chat window. I can use this to communicate with the educator and other participants of the conference just by typing in this box here and clicking Enter. In the center is the educator's lecture. Before we begin, I'm going to mute myself so that the other participants do not hear any background noise from my end.
Welcome to the lecture for today. So this is a message that I'm writing in the chat window. Are you all set?
I'm going to type in the chat window, yes, educator. I am.
Today's lecture, it's about metrics on compact Lie groups. But before we talk about that, we will talk about a topic which it's important, the differentiation of covariant tensor fields, and it's something that we would use later on. So that's what we would review now, the differentiation of covariant tensor fields. So differentiation of covariant tensor fields is the first topic that we will look at now. Okay. So tensor fields. Now let phi be a covariant tensor field of order R. So we have phi is a covariant tensor field of order R on the Riemannian manifold R. So we have it's of order R on the Riemannian manifold M. Okay. Now we want to define the notion of the derivative of the covariant tensor field. We already talked about derivatives of vector fields, okay. But now we want to define the notion of the derivative of the covariant tensor field. Okay. So that's the notion of the derivative of phi. So phi is a covariant tensor field of order R on the Riemannian manifold. Okay. Now, to do that, we will recall a notion that was used when we defined the covariant derivative of a vector field. So moving on to the next slide. Okay. Recall that for the derivative of a vector field x on M, so X is a vector field on the manifold M. So we have for the derivative of the vector field X on M, we use the notion of parallel transport. Okay. So that was the notion that was used when we defined the covariant derivative of a vector field. So we again are going to use that notion here. So we use the notion of parallel transport, and we'll use that same notion here. Okay. So the notion of parallel transport, okay, and that same notion will be used here. Now we will proceed this way. Now we will consider a C-infinity curve P of t on M. So P of t is a C-infinity curve defined on the manifold. So we use C-infinity for simplicity. The curve could be C1. It's sufficient, but just for simplicity, we just use this as a C-infinity curve on the manifold M. So we let P of t not be a fixed point on the curve. So P of t not is a fixed point on the curve. Okay. The curve. Now let's move to the slide and let's draw a picture to illustrate what we mean. So we have our manifold M, and we have our C-infinity curve P of t. We fix a point P of t naught of interest to us on the curve. So we have P of t naught on the curve, and we have another point P of t, where P of t is just an internal point on the curve. And then, okay. Now we will now let tau of t be the parallel transport along P of t from a fixed point P of t naught on the curve. So tau of t is the parallel transport from P of t naught to the point P of t. So we define a map. Tau of t goes from the tangent space at P of t naught M to the tangent space T P of t M. And tau of t is what we call the parallel transport. We already talked about that when we discussed covariant derivatives of vector fields. Okay. So we'll now define the covariant derivative of the tensor field is d field dt at t equal to t naught is equal to limit as t tends to t naught of 1 over t minus t naught into brackets tau of t star is a superscript phi at p of t minus phi p of t naught, and this is the definition of the derivative of a covariant tensor field on the Riemannian manifold. Okay. So now that we have talked about this, let's see whether the student has any questions to ask. Whether this definition makes sense. We see the student is unmuting themselves to talk. Okay. And
to ask a question, the student will raise her hand in this user's window. She will click the icon and wait to be acknowledged by the educator.
So we see the student has raised their hand.
Yes, Professor. I was wondering what tau star and onwards means.
Okay, to explain what the tau t star means, this is what we call the pullback map. We used that when we talked about the covariant derivative of vector fields. So start a new slide and to explain what that means. So recall that we defined the tau of t, the parallel transport map from t p of t naught m, which is the tangent space at p of t naught, to t p of t m. Okay. Now tau t star, the pullback map, what it does is that it takes a covariant tensor field that evaluated at the p of t and it gives you a covariant tensor field evaluated at P of T naught. So tau T star goes from T P of T M to T P of T naught M, and this is how it is defined. So you see it's the reverse map to tau of T. So tau T star, now when it acts on the covariant tensor field evaluated at the point P of T on the manifold, we take since phi is covariant tensor field of order R, so we take the arguments x1 through xr, and then so this is evaluated. So now the value of this tau T star phi at P of T naught, since it goes into the tangent space at P of T naught, so this we have phi of P of T evaluated at phi P of T, and then the argument is tau T star of x1 through tau T star of xr, where tau T star is the differential of the power transport map tau of T. So this is the pullback map that we define, and this is its explanation.
Yes, thank you.
Now we will end to this lecture, but what we'll do next week is that next week we will now apply the concept of the derivative of equivalent tensor field to the Riemann curvature tensor, and then we'll prove an interesting theorem of Cartan that relates the fact that if the derivative of the Riemann curvature tensor is 0, which means that the manifold is spiral, which means that that the Riemann curvature tensor is spiral to symmetric spaces. So we'll prove an interesting theorem that says that if the Riemann curvature tensor is spiral, then the space is locally symmetric. But that is all for next week. So this ends today's lecture.
The logout button is on the top right-hand corner. Click OK, and it brings you to the Transporter Educator's homepage.